Welcome back to It's Not Quantum Physics. Today we're going to look at transferring electrical energy. As always, we'll start with a quick quiz, checking our understanding from the last lesson. So 10 quick questions. Make sure you've got a piece of paper ready to write them down as we're going. So question 1, can you please draw me a symbol for a battery? So the circuit symbol for a battery. Question 2, can you write an equation down relating potential difference and current? Question 3, 4 and 5 are all on the screen now. Can you name the device, the component in the circuit that would give a VI graph for these three VI graphs? Question 6. Can you calculate, please, the charge if the current is 2 amperes and the time is 2 seconds? Question 7. Can you please also calculate the energy if the potential difference of the circuit that we've described in question 6, so current of 2 and time of 2, if the potential difference was 10 volts? Question 8, can you state the units for charge? Question 9, is velocity a vector or a scalar? And question 10, can you please tell me the number of electrons in the outer shell of aluminium? And a bonus mark if you can write down the electronic structure. Okay, well done. So hopefully you've had a go at all of those questions. Let's go through some answers. So question 1 asked us to draw the circuit symbol for a battery. Well, it is a cell that has got dotted lines between it, so it's an unknown number of cells. Question 2 is to write an equation that links potential difference and current. In this case, V equals I times R, otherwise known as Ohm's law. Question 3, if we look at the circuit diagram to our right here, you can see that first one has a 0 current in the negative direction of the potential difference and a small positive current once you get to a small positive potential difference. So this must be a diode, because a diode only allows the current in one direction, and that's the symbol for a diode. Question 4 and question 5 are both the same answer. They are both resistors, because they are both straight line graphs, so they're resistors. Which one has got the higher resistance and which one has got the lower resistance? Well, the lower resistance is the one that has a lower current for a higher potential difference, so that must be number 5, and number 4 then, sorry, let me get the right way around. If it's got a lower current for a higher potential difference, it is the higher resistor, so the higher value resistor. And if it has a higher current for the same potential difference, then it is a lower resistor, because that means you can get more current through, there's less stopping it. Question 6, we were told that the current is 2 amperes. And we were told the time is 2 seconds, and we need to work out Q. Well, hopefully remember that Q equals I times T, so that is going to be 2 times 2, which is 4. Now, I'm not going to write any units because we'll come back to that in a moment. Question 7 then. If the potential difference was 10 volts, then we had to remember E equals V times Q. So that's going to be 10 times 4, which is going to be 40 joules. Question 8. Q is measured in coulombs, capital C. Question 9, is velocity a vector or a scalar? It is a vector. Remember, the difference between a vector and a scalar is that a vector has a size and a direction, whereas a scalar just has a size. Okay, and so it matters which way your velocity is travelling. And question 10, the number of electrons in the outer shell of aluminium are 3, and the electronic structure is 283. And hopefully you've used a periodic table to check that. So total up what you got out of 10. If you've got 10 out of 10, fantastic. If you've got 9 or 8, brilliant, well done, keep checking. And if you've got 7, 6, 5, then make sure you go back and recheck that previous lesson. Right, so we'll move on to today's session, which is all about transferring energy. So we need to be able to do these 6 different things by the end of the lesson. We need to be able to describe the energy transfer, explain how unwanted energy transfers in wires can be avoided, recall the advantage of heating effect, recall the disadvantage of heating effect, explain the energy transfer in a resistor and where the energy goes, and use the equation to calculate the energy transferred. Now I'm going to start with a little video, and this video shows the different wires here having higher amounts of current flowing through them. So as you can see, as the amount of current increases, the temperature of the wire increases until the wire itself breaks. Now these are fuses, and we'll come back to these in a later lesson. But I thought it was really interesting to be able to see this process, because these are the electrons colliding with the ions in the wire. And the more electrons there are, the more they're going to collide and make those atoms vibrate, which causes it to heat up. So when we watched that video, what we were able to see is that those wires were getting hot, so there was an emission of thermal energy, and also we could see that they were changing colour, so there was an emission of light energy. Now I wonder if you can remember back from your earlier lessons, what type of diagram is this, and what could we actually calculate from it? Hopefully, as you've thought there, you remember that these are called Sankey diagrams, and the width of the arrow shows us how much energy is being transferred. So in fact, we could calculate the efficiency of our object using this. So here we can see we've got a large amount of thermal energy being emitted and a small amount of light energy being lost, and the thermal energy here would be the useful energy. So let's talk about what's actually happening inside of our wire, because this is really important to understand the process that's going on. So we're going to draw ourselves a model, and you might need a few different coloured pens in order to do this. And obviously pencil for your diagram. So we take our piece of metal, and here is our piece of metal in our circuit. So it's going to come out and it's going to go up to a point of potential difference. Remembering that this side is the positive side and this side is the negative side. So the electrons are going to want to flow to the positive side. Now, if we imagine that this wire is attached to our piece of metal, then we can see that the current will flow through it. Now inside of our metal, I'm going to colour them in green, we have got ions. And these ions are our atoms that have lost their free electrons. Because remember, those free electrons are now conducting around the circuit. Remember that those are the electrons that are in the outermost electronic shell. So here are all the ions, and in between those ions, holding them all together, remember from your chemistry lessons, those ions are being held together with electrons that are acting sort of as the glue, because remember, a positive and a negative is being attractive. So that electron, those electrons there, that sea of electrons, is pulling them together. Now those electrons are being attracted to the positive side of the battery. So those electrons are all starting to move, once the circuit is complete, in a direction towards the positive side. But some of those electrons are actually going to collide with our ions. And when those electrons collide with the ions, what we've actually got, and let's draw ourselves a sort of a more in-depth picture here. So there's my electron, here is my ion, and this electron is going to collide straight on with the ion. Well, it's going to cause that ion to vibrate. And as we know, a vibrating ion is actually something that has more thermal energy. So as the electrons collide with the ions, so they're colliding with the ions, they transfer energy, causing the material to heat up. Oh, not going to fit it on. So they cause that material to heat up. And so as that material heats up, more electrons are going to collide with it, causing it to heat up even more. So as we saw with those fuses right at the beginning, we're able to, well, in fact, the metal will melt because those ions are vibrating so much. So we can actually describe this model in words. So we've got 6 stages that we need to consider. Those electrons are flowing around the circuit going from negative to positive. So if I was to draw on my electronic current that's flowing around the circuit, it'd be from negative, where I've got lots of electrons, to positive, where I've got very few, hence why it's positive. Those electrons are colliding with the ions that are within the wire, and as they collide with it, they're transferring energy to those ions. And I've put here, it's through momentum, because the electrons have got a mass and a velocity, and the ions have got a mass and velocity. So it's a momentum transfer that causes those ions to vibrate more. Now, as the ions are vibrating more, as they're moving backwards and forwards more over here, that causes more electrons to collide with the ions, so the resistance is increasing again. So we see here that as more electrons collide with it, there's more resistance, so less current is going to flow. But that also means that there's a greater transfer of energy from our piece of material. So those electrons, those tiny electrons that are in our wire, are the ones that are causing our wire to heat up because they collide with those ions. So let's consider now how we could increase the current flow through our material and how we could reduce the resistance. And this is a higher question or higher concept that you need to consider if you're going to be doing the higher paper. So pause the video here and see if you can come up with some ideas as to how we can get more electrons through that wire. Okay, well done. Hopefully you managed to come up with some ideas. Well, let's go through some of the ideas you might have come up with. We could increase the thickness of the wire. If we increase the thickness of the wire, so here's a very thin wire, and here's a very thick wire, and we've still got our ions. I might only have one ion in each of these. Here I might have 2 ions. So if we increase the thickness, there are more paths for those electrons to travel without their collision, or without any collision. So that is kind of like if you've got a road and you have a traffic jam, opening up a road next to it is going to allow more cars to pass through. So it gives more routes for those electrons to pass through. Okay, there's our first one. Well, our second point, in fact, let's write that down. So thickness of the wire. So the thicker it is, the more current can flow. Okay, so the second one is related to the fact those ions are vibrating. If the ions are vibrating, then more electrons are going to collide with those ions. But how can we reduce that vibration? Well, we can reduce the temperature of the wire. If we drop the temperature of the wire, then the ions aren't going to vibrate as much, which means the electrons are not going to collide with them as much. So decreasing the temperature of the wire. Now the third way we can deal with this, the third way we can allow more current to flow through, is related to the material that we're using. And I've called this the intrinsic resistance. If you go to A-level physics, it becomes something known as resistivity, which is how well the material is at reducing that flow of current, how well it reduces the flow of current, how big the ions are, how mobile the ions are. Different ideas like that can change the way that material has its own resistance. Some materials have lower resistance and some materials have higher resistance. For example, if you look at some high quality headphones, you'll find that they have gold plated connectors, and that's because the gold has a lower resistance, so therefore more current can get through and drive those headphones. So it's all about reducing the resistance in your material. So the resistance of the material is our third idea to consider. And obviously copper, as I've mentioned here, has a lower resistance than other materials. So if we wanted to work out the energy that's transferred, we actually know an equation already. In our previous lesson, we have learnt, some pens here, E equals V times Q. We also know that Q, I'm going to get red again here, equals I times T. Two quite important equations that we've learnt so far. What about if everywhere where I've got a Q in this equation, I put I times T? Could we work out the energy that's lost depending upon the current, the time, and the potential difference? Well, yes, we can, because we can have E equals V times I times T, where everywhere we've had that Q, we put I times T because it comes from this equation here, Q equals I times T. So I can now work out how much energy is transferred in joules, remember energy is in joules, depending upon the potential difference, the current and the time. So in other words, how much energy the electron's carrying, how many electrons there are per second, and how many seconds there are. That's basically what we're working out here. And let's just look at the units for these as well. So E is energy transferred. And that obviously is in joules, capital J. V, as we've learned so far, is the potential difference. And that is in volts, or V. I is the current, and that is amperes, or capital A. And T is the time, and we always measure time in seconds, or lowercase s. So this will allow us to calculate that energy that is transferred. I think we should do an example to make sure we can use this equation correctly. So in our question here, we're told that we want to calculate the energy transferred when a 24 volt car battery, so I know that's V, so I'm going to write that down, supplies a current of 0.5 amps, so I is 0.5 amps, to a heater for 6 minutes. So 6 minutes is my time. And this obviously is going to be a problem because we're in minutes before we even start. So I know I can convert that because there are 60 seconds in a minute. So 6 times 60 is going to give me 360 seconds. Now I've got all my units in the correct form. I can put them into my equation. Now remember, we always write the equation first. E equals V times I times T. And we write that to make it stick in your head. It's really important to learn your equations. Now V we know is 24. I we know is 0.5. And T we know is 360. So all we need to do is to grab our calculators and put our numbers in. So 24 times by 0.5 times by 360. Hopefully you've done it on your calculator as well, and you should end up with 4,320 joules. So this tells us that this component is going to transfer 4,320 joules from the heater. So we'd lose 4,320 joules from the battery, and we'd lose 4,320 joules at the heater, hopefully as thermal energy. If it's 100% efficient, it's all thermal energy. If it's 50% efficient, then we might lose some from sound or from light. But we hope it's quite efficient, otherwise we're not going to get as much heating from it. Now I think it's going to be your turn to have a go at some questions. So there are 3 questions on the screen right now. I'll just make them a bit bigger for you. I'd like you to have a go at those 3 questions, get yourself some answers, and we'll go through the answers together in a moment. So pause the YouTube video here. Well done, ladies and gentlemen. Let's go through the answers together and let's have a go at making sure we've got them all correct and set out the use of our equation correctly as well. So question 1, we are told that we want to work out the energy. We don't know that, but we do know the potential difference is 12 volts. We do know the current is 4 amps, and we do know the time is 20 seconds. So we're going to write our equation down. E equals V times I times T. Put our numbers in. 12 times 4 times 20. Using our calculator, 12 times 4 times 20 is going to give us 960 joules. Now in a real exam, that could even be 3 marks there, just for doing that. Question 2, let's make sure we've done this one as well. So calculate the energy. Again, we don't know it. So this time we know it's a 6 ampere bulb. It's running on mains electricity, which we'll come to in a later video, which is 230 volts, and the time is 30 minutes. So first step is obviously to convert the time, and this will give you your first mark. So we're going to have 30 times 60, which is going to give us 30 times 60 is going to give us 1,800 seconds. So again, we're going to write our equation down. E equals V times I times T. Put our numbers in. We're going to have 230 multiplied by 6 multiplied by 1,800. And we're going to put that into our calculator and get our answer. So 230 times by 6 times by 1,800 is going to give me an answer of 2,484,000 joules. It's not a nice number that we use in physics, so we're going to do a bit of rounding and a bit of standard form. I'm going to take my decimal place from here and I'm going to place it here. So 1, 2, 3, 4, 5, 6 jumps. So this could be 2.484 times 10 to the 6 joules. But because we're going to round it, it's going to be 2.5 times 10 to the 6 joules. In fact, you could even have written it as 2.5 megajoules, because mega is 10 to the power 6. So there's question 2 completed. Let's have a look at question 3. So in question 3, this time we want to work out the current. So we're told we have the potential difference, which is 1.5 volts. We're told that it emits 450 joules, and that the time it's running for is 10 minutes. So hopefully again you've spotted that 10 minutes needs to be in seconds, so that's going to be 10 times 60, which is going to be 600 seconds. We're then going to write our equation down. Don't worry about rearranging at this stage, we can just put the numbers in, because remember that gets you your first mark. So putting your numbers in, so 450 is going to be equal to 1.5 times by I times by 600. Then we can do that first stage. We can say, well, what's 1.5 times by 600, which is 900. So I've got 900 times by I. So on both sides now, I need to divide by 900 to get I on its own. So it's going to be 450. Divide that by 900, which will give me I, which is in fact going to be 0.5 amperes. And remember, we underline our answers to make it easier for the examiner to deal with. So there we go, 3 examples of the questions that hopefully you'll have a go at later on. So the last thing we need to talk about in this lesson is what the advantages and disadvantages are of electrical heating. So where might we find electrical heating as an advantage? Well, one advantage of electrical heating is in fact an electrical fire. Where we want, or fireplace, where we want to heat up, or a heater, where we want to heat up a room or an object, we can use electricity to do this, and it's actually pretty good at doing it. If we want to melt steel, things like that, we can use very, very big coils of electricity to heat it up, of flowing current. So that is an advantage. We can heat things up quite efficiently. But one of the disadvantages of electrical heating is that in fact we have to dissipate it. So the energy is lost to the environment from our electrical component. So for example, you may know about computer processors. Well, computer processors generally have to have very, very big blocks of material on top of them. So it's a very, very small thing underneath is a computer processor. And then you put a massive block of almost copper sometimes on top, because you need to dissipate that heat. You need that heat to be able to escape, because otherwise it's going to get too hot and it's going to cause problems with the computer component itself. You may also find that when you have a mobile phone gets hot due to that electrical heating, and in fact can cause the battery to reduce quicker because you are having to work harder to get that current through. So there are some positives and there are some negatives to electrical heating, and we need to be aware of those two ideas. So let's just finish now by recapping and making sure we've covered everything we need to. So we're describing the energy transfer that takes place when a current passes through a resistor. We're going from electrical to thermal. Okay, it's going to get hot. That's the process. Explain how unwanted energy transfers in wires can be avoided. So that's the idea that we can increase or decrease resistance by increasing the width of the wire, the cross-sectional area of the wire, the length of the wire. Oh no, ignore the length of the wire. We can increase the cross-sectional area of the wire, so there's more routes for it to go through. We can reduce the temperature to try and reduce that unwanted energy transfer, or even just lower the current. We've looked at advantages and disadvantages of heating effect on electrical current, and we've explained where the energy goes when we've got a resistor that is getting heated up. And finally, we've looked at that equation, E equals V times I times T. So I hope this has been a useful video for you. Don't forget, if you want to, you can subscribe to the channel, and you can also like this video, and I will see you for the next video on electricity.